Hello there, Mr. Sutton here with the BC Calculus 7-6 Part 1 homework solutions on Lagrange Error Bound. For this problem, they want the Lagrange Error Bound when the second degree Maclaurin series is used to approximate sine of 10 to the negative third. So since they asked for Lagrange, we're going to give them Lagrange. So we can start with error less than or equal to big fraction. And now we need to figure out the interval that this is happening in. Since it's a Maclaurin series, our center is going to be 0, and our input value is 10 to the negative third, so we're going to find the max derivative from 0 to 10 to the negative third. Which derivative do we need? Well, it's second degree Maclaurin, so that means we need to go one higher on the degree for everything. So this will be the third derivative, third factorial, and we're going to have x absolute value to the third power. Now we need to find the max third derivative. Well, it would help if we knew what the third derivative was in general. If our original function is sine, then f prime is going to be cosine of x, f double prime is going to be negative sine of x, and f triple prime, which we'll be taking the absolute value of and maximizing, we're going to have absolute value of negative cosine of x. So what's the biggest value negative cosine of x can achieve on the interval from 0 to 10 to the negative third? Cosine of 0 itself is 1, so that would be negative 1, whose absolute value would be 1. Now, cosine is decreasing across this interval from 0 to 10 to the negative third. Cosine decreases between 0 and pi over 2 when your x values are getting smaller on the unit circle. So the biggest thing we can do is just plug in 0 for x, and that'll give us an absolute value of 1 when all is said and done. So 1 then, that's going to be this whole numerator. We have 1 over 3 factorial. And then for the x value, we're just plugging in the input 10 to the negative third. And we don't need absolute value anymore because that's positive. Let's just put this in the calculator and see what we get. So we have 1 over 3 factorial, 10 to the negative third to the third. And that is roughly 1.66. I'm going to round it up to 7. I always round up with these less than problems. 1.667 times 10 to the negative 10. On this problem, they want the Lagrange error bound when a linear approximation about x equals 7 is used to estimate f of 7.04 for this square root function. So let's write our error bound form. We have error less than or equal to big fraction. And then what's our interval on this one? Well, we're centered at 7 and estimating 7.04. So our max derivative is going to be between those two values. And which derivative do we need? If we have a linear approximation that we're using, that means we need second power and second everything else for the rest of this form. So we're going to have the second derivative, absolute value, 2 factorial down here, and then this is going to be x squared, but it's actually going to be x minus 7 squared because we have a center of 7. And I don't need the absolute value because I've got an even exponent. All right, now I need to find the max derivative. In order to do this, I'm actually going to need to know what the second derivative looks like. So I'm going to rewrite the original function as 1 plus x to the 1/2 power, just to make it a little easier to take some derivatives. Using my power rule now, I've got 1/2 times all this stuff to the negative 1/2. That gives me f prime. And now I need f double prime, so I'm going to go one more time on that power rule. So multiplying negative 1/2 by 1/2, I've got negative 1/4, 1 plus x to the, this will be negative 3/2 now. Now, since this is really a square root that's going on here, it's only going to return positive values. So when I take the absolute value of all this, I can just rewrite this, and I'm going to rewrite the whole form now. I'm going to have 1 over, and now I'm going to have 4 times the square root of 1 plus x cubed. So this is the radical rational form of what we have up here without that negative out in front, because again, this is returning only positive values. So how can I maximize this thing? Well, in order to make a fraction as big as possible, you want to make the denominator as small as possible, which means I have to plug in the smallest possible value for x. Well, the smallest possible value on this interval is 7. So I'm going to plug 7 in here, and I'm going to simplify this a tiny bit to 1 over 4 times the square root of 8 cubed. But otherwise, I'm just going to leave it the way it is because this is an exact value right now. All right, going back to my form here, this nastiness is what I have now for my numerator. I've got 2 factorial downstairs still, and I'll also plug in 7.04 for x at this point. And then let's just see what all this comes out to on the calculator. So it takes a little bit of a while to enter all this in here, but I needed two fraction forms. I had a fraction inside a fraction. Got everything there, though. And this comes out to about 8.83, 8 and some change. I'm actually going to round it up to 8.839 because I'm going to write less than here. And I've got 10 to the negative 6 power for that other piece of my scientific notation here. On this problem, we want the Lagrange error bound when approximating e to the 0.1 with this series here. So I'm going to write out my error bound form. We have error less than or equal to a fraction, and we have to figure out our interval of values. So where's this thing centered? Well, the key on this problem is recognizing that this is the Maclaurin series for a third degree polynomial version of e to the x. So that means we're centered at x equals 0. So I'm going from 0 to the input value, which in this case is 0.1 on the e function. So max from 0 to 0.1. Now which derivative do I need? This is a third degree Maclaurin, so that means we need fourth power and fourth derivative and everything fourth for the rest of this. Next number up. So fourth derivative of x, fourth factorial, and then we're just going to write x to the fourth as well. No absolute value needed because it's an even exponent. Now let's find that maximum derivative. Well, the fourth derivative of e to the x is the same as all the other derivatives of e to the x. It's just e to the x. So we're trying to maximize the absolute value of e to the x for this one. And e to the x is a nice increasing function for all real numbers, which means to make it as big as possible, you just plug in the biggest x value possible, which in this case is the 0.1 at the right side of our interval. So this max value is just going to be e to the 0.1. All of this has to be less than or equal to that. All right, going back to my form, I'm going to just plug in e to the 0.1 for my numerator. I've got 4 factorial downstairs, and I've got 0.1 to the fourth power out here. Time for the calculator. And plug in all that in. What do we get? About 4.605. We're going to round up always on these error-bound problems. So we'll say less than 4.605 times 10 to the negative 6. For this no calculator problem, we're told that f is a function that has all the derivatives in the world. P3 is our third degree polynomial to approximate that, about 0. And we're told that this series converges at x equals 1. Awesome. We're also given some information about the nth derivative of this function, but only for n values from 1 to 4, so that one's kind of limited. Of the following, which is the smallest k value for which Lagrange error bound guarantees f of 1 minus p3 of 1 is less than or equal to k? So basically, if we translate this, they're just asking for the Lagrange error bound for this f function, and we know about the derivative. We don't really know a whole lot else about the f function. But since Lagrange error bound is involved, let's go ahead and write out the form for that and hope for the best. So I can write error is less than or equal to some fraction. And in the top, I've got my max derivative. Now, what are my intervals here? Well, this polynomial is centered at x equals 0, so we're going from 0 to something. And it looks like they're plugging 1 in. This is basically just another way of saying error if we try approximating 1 with this polynomial. So our interval then is going to be from our center 0 to our input 1. And what order derivative am I using in my error bound? Well, we approximated with a third degree polynomial, so we need fourth derivative and fourth everything else. So absolute value of fourth derivative of x, fourth factorial, and x to the fourth with no absolute value needed because there's an even exponent. Now we need to figure out this max derivative up here. So in order to do that, we're told right here that the nth derivative is less than or equal to this expression. So we're actually just going to plug in 4 for n. So that'll give us 4 over 4 plus 1, which is to say our fourth derivative is no greater than 4/5. So that's a value we can go back to our overall form here now and plug back in. So I'm going to write 4/5 over 4 factorial, and then I've got 1 being plugged in for x because that was my input value. And this is essentially the k value that we're looking for. It's this expression right here. We just have to simplify it a little bit. So if I'm doing 4/5 divided by 4 factorial, well, that's really like multiplying by the reciprocal of 4 factorial, which is 1 over 4 factorial. this 1 to the 4th just kind of goes away because it's just 1. So we have 4/5 times 1 over 4 factorial. I could reduce this if I wanted to, but hey, I see this answer in one of my answer choices, choice B, so I'm just going to pick that and be done with it. For this no calculator problem, we're given this function sine of 5x plus pi over 4, and p of x we're told is the third degree Taylor polynomial for f about x equals 0. So based off of this, the first thing they want us to do is actually find this third degree Taylor polynomial. So for that, we're going to need to know the derivative, the function value. We need actually at least the first 3 derivatives to get this third degree polynomial. So let's start with f of 0. That's going to be sine of pi over 4 basically, because this 5x gets zeroed out. Sine of pi over 4, we can turn that into radical 2 over 2 if we want to make it into a number. Didn't actually have to simplify it, but we're going to. And then we need the derivative at 0. So that's going to be cosine of all this stuff evaluated at 0. Actually, it's going to be 5 cosine, right? Because you have an inner tail of 5 if you take the derivative of 5x plus pi over 4. So 5 cosine of all that. Now, the nice thing is every time you plug in 0, you're getting rid of this 5x term inside, and you're really just evaluating the trig function at pi over 4. So this is 5 times cosine of pi over 4. The other nice thing is cosine and sine of pi over 4 are the same thing, right? They're both radical 2 over 2. So this is just going to be 5 radical 2 over 2. Now the second derivative, that's going to be, let's see here, negative 25 sine of this stuff, evaluated at 0. So that's negative 25 times root 2 over 2. And our third derivative that we need for our third degree term, that's going to be, let's see here, negative 125 cosine of all that stuff. And this is really just negative 125 times root 2 over 2. So there we go. We've got 3 levels of derivatives plus the original function value. Now just using our general Taylor build-a-series formula here, we've got our first term, which is always f of the center, so in this case, radical 2 over 2, plus now we have the first derivative times x, or x minus the center, but in this case the center is 0, so it's just going to be 5 radical 2 over 2x that we're adding there. Next, we're going to be subtracting f double prime over 2 factorial. So this is going to be minus 25 radical 2 over 2 with a 2 factorial in the denominator also, and we're going to have an x squared there. And then finally, we're doing, this now is going to be f triple prime of 0 over 3 factorial. So we're going to have minus 125 root 2 over 2. 3 factorial will be in the denominator, and we'll have an x cubed out there. And there is p. We could simplify it, but why bother? On this part of the problem, they want the coefficient of x to the 22nd in the Taylor series about x equals 0. So in general, our coefficient of x to the 22nd should be the 22nd derivative at 0 over 22 factorial. So all we really need to do is figure out this 22nd derivative. Well, that seems like a lot of derivatives to take. So let's review what we've done so far in terms of derivatives and see if there's a pattern we can pick out. So just reviewing from the last slide what we got for our derivatives, the 0th derivative, in other words, just the function value itself, f of 0, that was radical 2 over 2. And then the first derivative at 0, that was 5 radical 2 over 2, followed by, let's see, negative 25 radical 2 over 2. And then finally, the last one we had to find for that last part of the problem was negative 125 radical 2 over 2. So there definitely is a pattern here. We keep multiplying by 5s, and every now and then we become negative 2 because we're switching between cosine and sine, and sometimes they're negative and sometimes they're positive. So this last one, the original function was sine, so it was positive, but then we had cosine, still positive, but then turned into negative sine, negative cosine. So we're going to be back to positive sine if we take another derivative, and multiplying by 5 again, that's going to give us 5 to the 4th, or 625 radical 2 over 2. And this pattern just keeps going. Now the key here, a few key things. First off, it's always 5 to whatever order derivative you're dealing with. Second, in terms of whether it's positive or negative, So it always goes positive, positive, then negative, negative. So if you can find where you are in this cycle, you can figure out the positive or negative piece. So let's just warp ahead a little bit, because we could do all these other ones, but we're just going to keep getting 5 to some new power in either positive or negative. If we go to the 8th derivative, that's going to be 5 to the 8th radical 2 over 2. It's also going to be positive. It's going to have the same positivity as the 0th derivative. And if we warp ahead even more, since these are going in increments of 4, all the way to the nearest multiple of 4 to 22, so the 20th derivative, that is also going to be positive. That's going to be 5 to the 22nd radical 2 over 2. Now let's go down 2 here. So the 21st derivative, also going to be positive, 5 to the 21st radical 2 over 2. And just do one more here, the 22nd derivative, that will now be negative. It's going to be in line with what the second derivative was, just following this pattern of 4. And this is going to be negative 5 to the negative 22 radical 2 over 2. So this ends up being our 22nd derivative. Now we're not quite done yet, because you actually have to put that in the numerator of this fraction up here, and then you'll have 22 factorial in the denominator. Or you could rewrite this if you wanted as negative 5 to the 22nd radical 2 over 2 times 22 factorial, either of those. For this part of the problem, they want us to use Lagrange Error Bound to show that this is the error between the true function and the polynomial they talked about earlier. They want us to show that this is less than 1/100th. Well, if they want Lagrange, let's give them Lagrange. So we'll start off with our general form here. We can say error is less than or equal to our big fraction here, and we need the max derivative on top. Now, what's the interval going to be? Well, since this was a polynomial that we're using here, since p is a polynomial about x equals 0, that's our center. So we're going from 0 to whatever number we're trying to plug in, which is 1/10 in this case. So from 0 to 1/10, we want the max derivative. Which derivative do we want? Well, since p is a third degree Taylor polynomial, we need the fourth derivative and fourth everything. So this will be fourth derivative of x. And then we want 4 factorial. And over here, we're going to have x to the fourth. No need for absolute value since we have an even exponent. Now let's find that max derivative. So recall that the third derivative, which we already found in part A, was negative 125 cosine of 5x plus pi over 4. So we need to find one more derivative, and then we'll figure out how to maximize its value. So one more derivative, that would be, let's see, positive 625 sine of 5x plus pi over 4. And we want to maximize the absolute value of this expression. Now, we can kind of hem and haw over, well, I'm only allowed to plug in numbers between 0 and 1/10, so if I'm only allowed to do that, what's the biggest this can get? And normally I would say, go to town on that reasoning, but we're just going to get a general kind of upper bound for this, and then if it's not good enough based on what they wanted us to show in the problem, which is what this was all less than 1/100th, if our numbers aren't good enough, we can go back to here and get a tighter number. But for now, let's just say that since sine and cosine can't exceed 1 for the value of the function itself, this whole absolute value can't be any higher than 625. I mean, it probably doesn't even get that high, but let's just call this our upper bound for now. So we'll say this is less than or equal to 625 times an upper value of 1 for sine. All right. So plugging that back in here, we have 625 over 4 factorial. And again, we may need to adjust this number later depending on whether or not we meet this threshold of error here. So we've got 625 over 4 factorial. And then x, that's just our plug-in value of 1/10 that we're raising to the fourth. Now, this is a no calculator problem. You have to show beyond a reasonable doubt that this is actually less than 1/100th. So how can we do that? Well, 4 factorial, that's really 4 times 3 times 2 times 1, which is 24. This is 24 times, this is going to be 10,000 here, 1 with 4 zeros after it. So that's going to be 24 with 4 zeros, 240,000 on the bottom, 625 on the top. And we could try reducing this, but there's really no need to reduce this, so waste time doing that. We just have to show that this fraction is less than 1/100th. So I'm going to round this 625 up to 1,000. 625 over 240,000 is definitely less than 1,000 over 240,000. So if I can show that this expression here is less than 100th, then I've already shown that my original expression is also less than 100th. So what is 1,000 over 240,000 if I reduce it? Well, that's 1 over 240. Now, comparing that easily to 1 over 100, we see that this has a larger denominator, so therefore it must be smaller, less than 1 over 100. So with a little bit of cleverness here, we've met our burden of proof. For this last problem part, they suddenly define a g function as the integral from 0 to x of the f function that we talked about earlier. They want us to write a third-degree Taylor polynomial for g about x equals 0. So one way to do this would be to take the antiderivative of this craziness up here and then construct a polynomial from scratch about 0. Another way, since you already have a third-degree polynomial for this thing, is just to take the first 2 degrees of this and integrate it. So we're going to say p of x, we'll call this p2 of x actually, is equal to really just the first 3 terms of what we wrote in part A. So root 2 over 2, we have 5 root 2 over 2x, and then the rest of this here. Now the reason I'm only writing out up to the x squared is because I know when I take the antiderivative of all this, I'm going to end up with an x to the third power, and they wanted a third-degree Taylor polynomial for g. So I only need 2 degrees to get to the 3 when I integrate. So now going ahead and taking this antiderivative, g is just going to be the antiderivative from 0 to x of this p sub 2 of t here that I've got. Now I could actually take the antiderivatives in terms of t and then plug in x and plug in 0 and subtract. But I notice that when I do this, all of my terms are going to have t's in them. So when I plug in 0 for t, it's going to zero out everything in the second half of that little FTC subtraction thing that I do. So instead of doing that whole dance, I'm just going to go straight to plugging x into the antiderivatives. So this first one, this is going to be root 2 over 2x. Next, we bump this up to an exponent of 2 and divide. So this is 5 over 4 radical 2 x squared. And then finally, this one, I bump it up to a 3, divide. So I have 25 over 12 radical 2 x to the third.